Before we dive into exponents, let's quickly remember what a numerical expression is. Think of it as a mathematical phrase. It uses numbers and operation signs like plus, minus, times, or divide. A key thing to remember is that an expression does not have an equal sign. It's not a complete equation. It's a value waiting to be calculated. For example, 5 plus 3 is an expression. When we start working with exponents, we're just adding a powerful new tool to the expressions we already know how to work with. An exponent is like a shortcut for a really long multiplication problem. Imagine you had to write 2 times 2 times 2 times 2 times 2. That's a lot of 2's. Instead, an exponent lets you write that much more efficiently. It tells you exactly how many times a number should be multiplied by itself. It saves time, space, and makes it much easier to read large numbers in scientific notation or when dealing with big, real-world problems. Every expression with an exponent has two main parts. The large number, which is called the base, is the number that gets multiplied. The small raised number is the exponent, and it tells the base how many times to multiply itself. For instance, in 2 to the power, the number 2 is the base, and it is the factor you will use. The number 4 is the exponent, and it tells you to use the base as a factor 4 times. Every expression with an exponent has two main parts. The large number, which is called the base, is the number that gets multiplied. The small raised number is the exponent, and it tells the base how many times to multiply itself. For instance, in 2 to the power of 4, the number 2 is the base, and it is the factor you will use. The number 4 is the exponent, and it tells you to use the base as a factor 4 times. The most important part is figuring out what an exponential expression is actually worth, or what we call evaluating it. To evaluate, you simply write out the repeated multiplication and then calculate the result. For example, let's look at 3 to the power of 4. You would expand that to 3 times 3 times 3 times 3. You always work the multiplication from left to right. 3 times 3 is 9. Then 9 times 3 is 27. And finally, 27 times 3 is 81. The value of 3 to the power of 4 is 81. Let's try a quick example. If you see the expression 4 to the power of 3, you know the base is 4 and the exponent is 3. This means you need to multiply the base by itself 3 times. Write it out as 4 times 4 times 4. You first calculate 4 times 4, which is 16. Then you take that 16 and multiply it by the last 4. 16 times 4 gives you 64. So the value of the expression 4 to the power of 3 is 64. Powers of 10 are special, and they're really easy to calculate. Look at 10 to the power of 5. You could write out 10 times 10 times 10 times 10 times 10. But there's a trick. The value of the exponent tells you exactly how many zeros follow the 1. Since the exponent is 5, you write the number 1 followed by 5 zeros. That gives you 100,000. This pattern makes powers of 10 essential for our number system, especially in science and engineering. This is the number one mistake students make with exponents, so listen closely. An exponent does not mean you multiply the base by the exponent. For example, 5 to the power of 3 does not mean 5 times 3, which is 15. That is incorrect. Instead, remember the exponent is a counter for how many times the base is used in multiplication. The correct way is 5 times 5 times 5, which equals 125. Always expand the expression in your head or on paper to make sure you're doing repeated multiplication. What about exponents of 0? This can seem a little strange, but there's a simple rule. Any number, like 8 or 100, raised to the power of 0 will always equal 1. So 8 to the power of 0 is 1, and 100 to the power of 0 is 1. The only tricky exception is 0 to the power of 0, which usually isn't covered in the 6th grade because it's considered undefined in most contexts. For now, just remember that any non-zero number to the power of 0 is 1. Now let's practice going the other direction. What if I give you the repeated multiplication and you have to write the shorthand exponential expression? Suppose you see the problem 5 times 5 times 5 times 5 times 5. The number being multiplied is 5, so that's your base. How many times is the 5 used? 6 times. So you would write this expression as 5 to the power of 6. It's all about counting the factors and identifying the number that is repeating. Expressions don't always contain only one exponent. Sometimes you'll have an exponent mixed in with addition, subtraction, multiplication, or division. For example, 2 to the power of 3 plus 5. When this happens, we have to use a specific set of rules to make sure everyone gets the same answer. You must evaluate the exponent first. In our example, 2 to the power of 3 is 8. So the problem becomes 8 plus 5, which equals 13. These rules for calculation are called the order of operations, and we use the acronym PEMDAS to remember them. P stands for parentheses, which always come first. Next is E for exponents. That's our new step. After that, you handle multiplication and division, working from left to right. Finally, you do addition and subtraction, also from left to right. Exponents are high on the priority list, which is why we must calculate them before any simple addition or subtraction. Let's see PEMDAS in action with an expression. 3 to the power of 2 plus 4 times 2. Step 1 is the exponent. 3 to the power of 2 is 9. The expression is now 9 plus 4 times 2. Step 2 is multiplication. 4 times 2 is 8. Now we have 9 plus 8. Step 3 is addition. 9 plus 8 is 17. By following the order of operations, we calculated the value of the entire expression to be 17. Parentheses also affect how an exponent is calculated. Remember, parentheses are the P in PEMDAS, so they're always first. If you see the exponent outside the parentheses, you must calculate the result of the expression inside the parentheses first. It changes the entire problem. For example, parentheses 2 plus 3 close parentheses to the power of 2 is very different from 2 plus 3 to the power of 2. The parentheses tell the exponent what its base really is. Here's a challenging example. Parentheses 5 minus 2 close parentheses to the power of 3 divide by 9. We start with P for parentheses. 5 minus 2 equals 3. The expression is now 3 to the power of 3 divide by 9. Next is E for exponents. 3 to the power of 3 is 3 times 3 times 3, which is 27. The expression is now 27 divided by 9. Finally, D for division. 27 divided by 9 is 3. So, the value of the expression is 3. We can use our ability to evaluate exponents to compare different numerical expressions. When comparing, you'll use the less than sign, which looks like the symbol for less than, or the greater than sign, which looks like the symbol for greater than. Let's try to compare 2 to the power of 5 and 5 to the power of 2. At first glance, the numbers look similar, but remember, the position of the base and exponent matters. We have to evaluate both expressions to see which one has a larger value. To compare 2 to the power of 5 and 5 to the power of 2, we first evaluate 2 to the power of 5. That's 2 times 2 times 2 times 2 times 2, which equals 32. Next, we evaluate 5 to the power of 2. That's 5 times 5, which equals 25. Now we compare the values, 32 and 25. Since 32 is bigger than 25, we know that 2 to the power of 5 is greater than 5 to the power of 2. we would write the comparison using the greater than sign. Exponents pop up constantly in the real world, especially in geometry. Think about finding the area of a square. If a side is s, the area is s times s, which we write as s to the power of 2. That's why we call s to the power of 2 s squared. Now think about a three-dimensional cube. Its volume is side times side times side, written as s to the power of 3. This gives volume its name, s cubed. You're using exponents every time you calculate area or volume. Exponents also model growth that increases by multiplication, which is known as compound growth. Imagine you deposit money in a bank and it grows by 2% every year. The formula for your money after several years involves an exponent. Or, think about a population of bacteria that doubles every hour. If you start with 10 bacteria, after 4 months, the population will be 10 times 2 to the power of 4. Exponents help us predict these large, rapidly increasing numbers. To wrap up, remember the 3 most important things from this lesson. First, exponents are just a shortcut for repeated multiplication of a number by itself. Second, always identify the base and the exponent correctly. And third, when evaluating expressions with multiple operations, remember the order of operations, or PEMDAS, and always calculate the exponent before you do simple addition or subtraction. Master these rules, and you'll be an expert at numerical expressions with whole number exponents.